So this lesson's on double integrals, but before we do that, let's remind ourselves of what a single integral was. If I had, for example, the integral from a to b of f of x dx, what is that? What does that represent? Well, a to b is an interval. We're integrating over that interval. F of x, y equals f of x, is some function above that, typically. At least when we're coming up with the concept the first time, we think of it above. And then f of x is the height. dx is thought of change in x. Height times change in x would give us what? If this is the change in x here and that's the height, that would give us the area. And then the sum, the s really means sum, that gives us the area under the curve. So a single integral is in essence an area under a curve. Now, what will a double integral be? So I want you to consider the plane g of xy equals 5 plus x plus 2y. So let's visualize that first. So we see the plane here. We see x coming out. We see y going left to right. And that is a plane that goes infinitely in all directions. We could zoom this out more if we like to get a feel for just how big this thing gets. It gets quite big. So that's what we're starting with. We're starting with that plane that is analogous to our curve that we showed last time. So now what do I want to consider next? I want to let omega be the rectangle defined as x is between 0 and 4 and y is between 0 and 2. So let's visualize that. So here's our region. X goes from 0 to 4 and y goes from 0 to 2. And then we had that plane. So we're looking for something under that plane above that region. What would that something be? If we go up from this little region up to the plane and sum everything up, what are we measuring there? This notation may help. We're taking the double integral over the region omega of g of xy, that'll be the height of the plane, dA change in area. The height times the area would give me what? Height times area would give me volume. So we're imagining we're stacking blocks. We're going to find the volume of all these blocks and add them together to approximate this double integral over omega of g of xy dA. So again, what this represents is the volume of the solid above the region omega, but under the function g of xy. So here's the solid we're creating above our region, and then we see the plane coming down. What will the volume of that solid be? That's what our question is going to be. What is the volume of the solid going to be? Well, how can we approximate that? If we remember back in Calc 1, our technique was to make rectangles. We approximated the area under the curve by taking a group of rectangles. Well, these aren't going to be rectangles. These are going to be blocks. We're going to have a small thing here in omega, and then it's going to have height. So we're going to imagine we're stacking Lego towers on top of each other to determine the approximate volume we're working with. So we are starting with this function, g of xy is 5 plus x plus 2y. Let me make that correct. And we have the region omega, which was 0 less equal x less equal 4, 0 less equal y less equal 2. So I want to kind of build that region omega if I can, and I'm going to separate it into multiple small. So I'm subdividing omega into these 8 pieces, and I want to find the midpoint of each of those 8 pieces. So what will those midpoints be? So the midpoints here are the x values, a half, 1.5, 2.5, 3.5, a half, 1.5, 2.5, 3.5. So those are the x values for the midpoints of those 8 rectangles. Again, notice I have on the spreadsheet a half, 1.5, 2.5, 3.5, a half, 1.5, 2.5, 3.5. On the bottom part, those rectangles went from 0 to 1. So the midpoint there, the y value would all be 0.5 for those 4. And then the ones above it, that goes from 1 to 2. So their midpoints would be 1.5. So these would be all of the midpoints. So let's take a quick look so you can convince yourself of that, right? In the y value, a half, a half, a half, a half up here, 1.5, 1.5, 1.5, 1.5. So I have all 8 rectangles with their midpoints. Now let's do some analysis with those. I'd like to know what the height is. So the height, that's my g of xy, is 5 plus x plus 2y. So let's go ahead and do a little spreadsheet programming. 5 plus x plus 2 times the y value. Let's add all those up. Now, let's think about the area of each of these rectangles. Well, width is 1, height is 1, 1 by 1. Width is 1, height is 1, 1 by 1. All of those rectangles have area 1. So we're putting a Lego block on each one of those. But the area of each of those is size 1. They just have different heights. Now, the volume is the height times the area. Area is length times width. And then we have height. So length times width times height will give us the volume of the Lego block we're going to stack. Which, this is certainly easy. Multiplying by 1 doesn't take a whole lot of work for us or for a spreadsheet. And you can see that the biggest Lego block will be rectangle 8, which will go up 11.5 units tall. But then what's my total volume going to be? Volume is going to equal the sum of that column, and then what do we get? 72. So what is our conclusion on this? The double integral over omega of g of xy dA is 72, which of course represents the volume of this thing. So the volume of this thing over that region of interest, that volume of that thing is 72 units. Now, how can we evaluate this algebraically? We've used graphs, we've used spreadsheets. Luckily, this one is relatively easy for us to do. So this is what we're working with, double integral over omega of g of xy dA, where omega is defined by x from 0 to 4, y from 0 to 2. But we're going to write this in a slightly different way. What was g of xy? G of xy was 5 plus x plus 2y. Now, what did y range from? Y ranged from 0 to 2. So I usually write it this way. Y ranged from 0 to 2. That's how y is changing. That's the change in y. And then what is x ranging from? X ranges from 0 to 4. That is the change in x. Notice this is the height times the length times the width, giving us volume. And these s's stand for sum. We're summing height times length times width, summing up the volume to give us the total volume of that surface under the plane above that region omega. So luckily, this one's relatively easy. We start with the inner integral. So the inner integral is the integral as y goes from 0 to 2 of 5 plus x plus 2y dy. And then using our fundamental theorem of calculus, thinking of y as the variable, that would give us what? That would give us 5y. Plus, if x is perceived as a constant, the integral would be xy. Integral of 2y would be y squared, as y ranges from 0 to 2. This, again, is my inner integral. So my inner integral is plugging in 2. 5 times 2 plus x times 2 plus 2 squared minus 5 times 0 plus x times 0 minus 0 squared. And then my inner integral is 10 plus 2x plus 4. So my inner integral is 14 plus 2x. Now, what does that correspond to? That's all of this stuff on the inside, which leaves us what then for our outer integral? Our outer integral will be, as x goes from 0 to 4, of 14 plus 2x dx. Well, what's my antiderivative there? This is now one variable calculus stuff. Antiderivative of 14x, antiderivative of 2x, x squared, evaluated as x goes from 0 to 4. So what does my integral become? 14 times 4 plus 4 squared minus 14 times 0 plus 0 squared. 56 plus 16 is 72. And that is exactly the same as what we predicted. Now, that doesn't usually happen. So it just so happens in this case because we have a plane that is linear. The midpoint was sort of the perfect point to choose to approximate how high that thing should be. So again, I want to emphasize 72 is the volume under that plane over that region. But there's one more thing I need to tell you about notation that sometimes causes trouble. So this is the way that I wrote it, but this is not typical. This is not traditional. I want to emphasize a couple things, though. The inner variables have to match. Notice y goes from 0 to 2. dy is on the inside. We like to have dy on the inside if we have a choice. X goes from 0 to 4. dx is on the outside. But the way this is written in most textbooks is they leave off those x's on the outside. So the way you will see this most places is in this form. And you just have to recognize, since dy is the first differential here, this stands for y equals 0. And since dx is the second one, the outer is dx, the outer here is x. But again, I often put the x and y in for emphasis.